Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles. Those two circles have internal length between them at this point. Let's call this point point N. Actually, the circles touch each other at point N. They have internal length at point N. And we also know that AB is the diameter of the big circle, and AC equals to 9 units, BD equals to 4 units, and this is a right angle, and this angle also equals to 90 degrees. And also we know that the small circle has 3 tangents. This is a tangent to the circle, and this tangent is tangent to the circle at this point. Let's call this point point S. Again, the tangent is tangent to the circle at point S. Point S is the point of contact between the circle and the tangent to the circle. And we have also the second tangent. This tangent is tangent to the circle at this point. Let's call this point point Z. So this tangent is tangent to the circle at point Z, or point Z is the point of contact between the circle and the tangent to the circle. Okay? And we have third tangent to the circle, and the point of tangency between the tangent and the circle is at this point. Let's call this point point M. Again, the tangent is tangent to the circle at point M, or point M is the point of contact between the tangent to the circle, and we will also define the center of the small circle as point Q. Again, point Q is the center of the small circle, and we will define the center of the big circle as point P. Point P is the center of the big circle, and we will define small r as the radius of the small circle, and we will define capital R as the radius of the big circle. Okay, so I will write down all the definitions. So Q, point Q is the center of the small circle and point P is the center of the big circle, and we also defined small r as the radius of the small circle, and we defined capital R as the radius of the big circle. Okay, so I will read again the things that I wrote. Point Q is the center of the small circle. Point Q is the center of the small circle. Point P is the center of the big circle. This point P is the center of the big circle, and capital small r is defined as the radius of the small circle, and capital R is defined as the radius of the big circle. Okay, and we want to find out the radius of the small circle. So we have here 3 points of tangency between the circle to the tangent of the circle. This is the first point of tangency between the tangent and the circle, point S. Point M is the second point of tangency between the circle and the tangent, and point Z is the third point of tangency between the circle and the tangent. Okay, so in the next step I will draw 3 radiuses to the points of tangency of the small circle. Okay, so this will be the first radius, this will be the second radius, this small r of course, and this is the third radius to the point of tangency between the circle and the tangent to the circle. Okay, and actually we have a rule, I will call it rule number 1. According to rule number 1, the tangent to the circle is perpendicular to the radius at the launch point. I will read rule number 1 again. According to rule number 1, the tangent to the circle is perpendicular to the radius at the launch point. Okay, so what is the meaning of rule number 1? Actually, rule number 1 states that if you draw a radius that is drawn to the launch point, then the tangent will be perpendicular to the radius. So here the radius is drawn to the launch point. Actually it touches the launch point. Point S is the launch point, or the point of tangency between the circle and the tangent to the circle. So we have radius that is drawn to the point of tangency, or to the launch point. Actually it touches the launch point. Therefore, according to rule number 1, the tangent to the circle is perpendicular to the radius at the launch point. So the radius is drawn to the launch point, therefore the tangent is perpendicular to the radius. That is to say, this angle is a right angle. So whenever you draw a radius that touches the launch point, that is drawn to the launch point, then the tangent will be perpendicular to the radius. That is to say, this angle is a right angle, it equals 90 degrees. And here also we have a radius that touches the launch point, that touches the point of tangency. So therefore, according to rule number 1, the tangent is perpendicular to the radius. That is to say, this is a right angle, and also this is a right angle, it equals to 90 degrees. Okay, we actually drew a radius to the launch point. Therefore, according to rule number 1, whenever you draw a radius to the launch point, then the tangent will be perpendicular to that radius. So this is a right angle, and also this angle equals to 90 degrees. And again, here we have a radius that is drawn to the launch point. Actually it touches the launch point. Therefore, according to rule number 1, the tangent to the circle, this tangent to the circle, is perpendicular to the radius at the launch point. The radius touches the launch point, therefore the tangent is perpendicular to that radius. This angle is 90 degrees. And also this angle is 90 degrees. Okay? And we know it is given us in the question that this is a right angle, so this is also must be a right angle, because the sum of the angles in a straight line equals to 90 degrees. So if this angle is 90 degrees, the other angle must complete to 180 degrees. So this must be also a right angle, and we know that this is a right angle that is on a straight line. So the other angle must be also a right angle in order to complete the sum of the two angles to 180 degrees. Okay, so we actually proved that the quadrilateral QZMD has 3 right angles, and we have a rule number 2, that states that the sum of the angles in a quadrilateral equals to 360 degrees. Okay, so I will write it down. Rule number 2 states that the sum of the angles of a quadrilateral equals to 360 degrees. Okay, so I will read rule number 2 again. According to rule number 2, the sum of the angles of a quadrilateral equals to 360 degrees. So actually we know that in quadrilateral QZMD we have three angles that are right angles. Okay, and 3 times 90 degrees is 270 degrees. And the fourth angle must complete the sum of the four angles to 360 degrees. So the fourth angle must be equal to 360 degrees minus 3 times 90 degrees. That is to say, it must be equal to 360 degrees minus 270 degrees, because of the fact that the sum of the four angles must be equal to 360 degrees, and we have already 270 degrees. The fourth angle must be equal to 360 degrees minus 270 degrees. That is to say, the fourth angle of quadrilateral QZMD must be equal to 90 degrees. That is to say, the fourth angle must be equal to a right angle. So actually we proved that quadrilateral QZMD has four right angles. Okay, I write it down. Quadrilateral QZMD has four right angles. And we have rule number 3 that states that if a quadrilateral has four right angles, then it is a rectangle. Rule number 3 states that if a quadrilateral has four right angles, then it is a rectangle. So I will read rule number 3 again. rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle. Okay, and we actually proved that quadrilateral QZMD has 4 right angles, therefore quadrilateral QZMD is a rectangle. Okay. Okay, so I will write down that quadrilateral QZMD is a rectangle according to rule number 3. Okay, quadrilateral QZMD is a rectangle according to rule number 3 because of the fact that it has 3 right angles. Okay, so we have rule number 4 that states, according to rule number 4, the opposite sides of a rectangle are equal to each other. According to rule number 4, the opposite sides of a rectangle are equal to each other. Okay, that is to say QZ equals to MD and also QM equals to ZD. So we know that according to rule number 4, side QZ equals to the opposite side MD. QZ equals to MD according to rule number 4. Again, QZ equals to MD according to rule number 4. But we know that QZ is the radius of the circle. So we can write here that QZ equals to small r, that is the radius of the small circle. So we can derive from this equality that MD equals to R. Okay, so MD is also the radius, equals to the radius of the small circle, and actually we will repeat on the same process on quadrilateral SQCM. Okay, so on quadrilateral SQCM we have 3 right angles, and according to rule number 2, the sum of the angles in a quadrilateral equals to 360 degrees, and we have already 270 degrees. So the fourth angle must complete the sum of the angles to 360 degrees. Therefore, the fourth angle must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral SQCM to 360 degrees. So the fourth angle must be equal also to 90 degrees. And we have rule, so quadrilateral SQCM has 4 right angles. And we have rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. So SQCM has 4 right angles, quadrilateral SQCM has 4 right angles, therefore according to rule number 3, it is a rectangle. And we have rule number 4 that states that the opposite sides of a quadrilateral are equal to each other, and we know that, so SQ is opposite to CM, so SQ equals to CM, and SQ equals to R, so CM also must be equal to small r. Okay, CM equals to R. Okay. In the next step, we will define line segment PM as X. That is to say, PM equals to X. Okay? PM equals to X. According to our definition, PM equals to X. So what is the value of CP? The value of CP will be equal to CM minus PM. Okay, CP equals to CM minus PM. Very simple. CP equals to CM minus PM. Okay, CP equals to CM minus PM. But what is the value of CP? CP, we have already proved that. What is the value of CM? We've already proved that CM is the radius of the small circle. So CM equals to small r, and PM equals to X according to our definition. Okay, so actually we got that CP equals to R minus X because CM equals to small r and PM equals to X. So CP equals to R minus X, small r minus X. So we can write here that CP equals to R minus X. Okay? Then we will create equation number 1, that is the calculation of the value of the radius of the big circle. Actually, the center of the circle is at point P. So AP equals to the radius of the big circle. AP equals to the radius of the big circle, capital R, because of the fact that P is the center of the big circle. So AP is the radius of the big circle. AP equals to capital R. And so that will be our first equation. So what is the value of AP? AP equals to AC plus CP. Okay? AP equals to AC plus CP. AP equals to AC plus CP. Okay? AC plus CP. AP, that is the radius of the big circle, equals to AC plus CP. What is the value of AC? AC equals to 9 units. It is given us in the question. And we have already found out that CP equals to R minus X. Okay, so CP equals to R minus X. Okay, so we found out that AP, that equals to the radius of the big circle, equals to 9 plus small r minus x. So I will write again the equation number 1. It states that the radius of the big circle equals to 9 plus small r minus x. Okay, we got the equation number 1 that states that the radius of the big circle equals to 9 plus small r minus x. But we also know that the radius of the big circle is also PB. Okay, the radius of the big circle is also PB because AB actually is the diameter of the big circle. It equals to 2 times r. AP is the first r and PB is the second r. So in total AB equals to 2 times capital R. So PB also is also the radius of the big circle. So that will be our second equation that states that PB equals to the radius of the big circle and what is the value of PB? PB equals to BD plus MD plus PM. Okay, PB equals to PM plus MD plus DB. Okay, PB equals to PM plus MD plus DB. Again, PB equals to PM plus MD plus DB. Okay, PB equals to PM plus MD plus DB. Okay, and what is the value of PM? PM equals to X according to our definition. The value of MD, we have already found out that the value of MD is the radius of the small circle, so it equals to small r plus dB. dB equals to 4 units because it is given us in the question. So in total we will get that PB equals to r equals to X plus small r plus 4 units. That is actually the radius of the same big circle. So we can write down that the radius of the big circle, equation number 2, equals to X plus R plus 4 units. Okay, we calculated the radius of the big circle from the other side of the circle, and we found out that the radius of the big circle equals to X plus small r plus 4 units. Okay, but we have already found out, according to equation number 1, that the radius of the big circle equals to 9 plus small r minus x. Okay, the radius of the big circle equals also to 9 plus r minus x. Okay, so we can compare equation number 1 to equation number 2, and we will create equation number 3. Actually, it is the equation number 1 and 2 are the expressions of the radius of the same circle, so those two expressions are equal to each other, so we can write down that x plus small r plus 4 equals to 9 plus small r minus x. Okay, we compare the equation number 1 to equation number 2, r equals to r. So here we have x in this side, we have r in this side of the equation, and we have r on the other side of the equation, so r is cancelled. So what left after we cancelled r? What is left is that x plus 4 equals to 9 minus x. Okay, x plus 4 equals to 9 minus x. Here we will subtract 4 from equation number 3, and we will get that x equals to 5 minus x. So we got that x equals to 5 minus x. Here we will add minus x to this equation number 3, and we will get that 2 times x equals to 5. Okay, we got that 2 times x equals to 5. Here we will divide the equation number 3 by 2 in order to get the value of x. So x will be equal to 5 over 2. 5 over 2 is 2.5 units. So actually we found out the value of x. So we have an equation, in equation number 1 states that the radius of the big circle equals to 9 plus small r minus x. Okay, the radius of the big circle equals to 9 plus small r minus x, but we have already found out that x equals to 2.5 units, so we can substitute x by 2.5 units, and so we do it, and we will get that r equals to 9 plus small r minus 2.5 units, and so capital R equals to 9 minus 2.5 is 6.5 plus small r. Okay, so we got that the radius of the big circle equals to 6.5 plus small r. You can say that the radius of the big circle is bigger by 6.5 units from the radius of the small circle, and we have we have already found that x equals to 2.5 units. Okay, so in the next step I will present a rule number 5, and we will implement rule number 5 in our circles. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. So I will read rule number 5 again. Rule number 5 states that if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay? So whenever we have two circles that touch each other internally, like in our example, then the distance between their centers will be the difference between their radiuses. Okay, so actually here we have two circles with internal length between them at point N. They touch each other internally at point N. Therefore, according to rule number 5, the distance between their centers, the center of the small circle is at point Q, and the center of the big center of the big circle is at point P. So the distance between the centers is exactly PQ. Okay, PQ, QP is the same. So the distance between their centers, according to rule number 5, will be equal to the difference between the lengths of their radiuses. The length of the radius of the big circle is capital R, and the length of the radius of the small circle is small r, so the difference between the radiuses will be capital R minus small r. So we got equation number 4 that states that PQ equals to capital R minus small r. Okay, here we will add r to equation number 4 and we will get that capital R equals to PQ plus R. Okay, capital R equals to PQ plus R. Okay, we have expression for the radius of the big circle, but in equation number 1 we found out the expression for the radius of the big circle. We found out that the radius of the big circle equals to 6.5 plus small r. Okay, so we have two expressions of the same radius of the big circle, so we can compare between them. Question number 5 will be the comparison between the two equal equations that is the expression for the radius of the big circle. So PQ plus small r equals to 6.5 plus small r. We compared the two equal equations for the radius of the big circle. We got this equality. Here we have r, small r in this side of the equation, and we have small r in the other side of the equation, so we can cancel r. After we cancelled r, we got the value of PQ. Actually, we found out that PQ equals to 6.5 units. That is actually the distance between the centers of the two radiuses. And we have already found out that x equals to 2.5 units. Okay? So here we will connect together points P and Q by a straight line. Actually, we created a right triangle because of the fact that this is a right angle. QMP is a right angle, therefore triangle QMP is a right triangle. So in triangle QMP, we know the value of the hypotenuse, it equals to 6.5 units. We know that PM equals to x and x equals to 2.5, and the only missing variable is QM, that is the radius of the small circle that we are looking for. So we can use the Pythagorean theorem in order to find out the radius of the small circle. So according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is qp squared equals to the sum of the squares of the perpendiculars equals to pm squared plus mq squared. Okay, so here we implemented the Pythagorean theorem in the right triangle QMP. Okay, again we implemented the Pythagorean theorem in triangle QMP. According to the Pythagorean theorem, the square of the hypotenuse, that is to say qp square, equals to the sum of the squares of the perpendiculars equals to pm square plus qm square. But we know that qp equals to 6.5 units, so qp square is 6.5 square, and we know that pm equals to x and x equals to 2.5 units, so pm square is 2.5 square equals to mq square. Mq is the radius of the small circle, mq equals to r, so mq square is r square. So we got this equality that states that 6.5 square equals to 2.5 square. 6.5 square equals to 2.5 square plus r square. Okay, 6.5 square is 42.25 units. And 2.5 square is 6.25 units. Okay, plus r square. We got that 42.25 equals to 6.25 plus r square. Here we will subtract 6.25 from this equality, and we will get that r square equals to 42.25 minus 6.25 is 36. So we got this equality that r square equals to 36. We will take a root out of this equality, and we will get that the radius of the small square equals to the root of 36 equals to 6 units. Okay, so the answer to the question is that the radius of the small circle equals to 6 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of the small circle, and we have here two circles with internal length between them at point N. They touch each other at point N. And we also know that AC equals to 9 units, BD equals to 4 units, and this is a right angle, and this is also a right angle, and the small circle has 3 tangents, and we want to find out the radius of the small circle. So first of all we defined point Q as the center of the small circle and point P is the center of the big circle, and we also defined small r as the radius of the small circle and capital R as the radius of the big circle, and then we drew three radiuses of the small circle that touch the point of tangency of the three tangents. This radius touches the circle at point S. This radius touches the circle at point M, and this radius touches the circle at point Z. It is actually the point of tangency between the tangent to the circle. So all the three radiuses touch the circle at the point of tangency or at a launch point. Okay, and we have rule number 1 that states that the tangent to the circle is perpendicular to the radius at the launch point. Okay, the tangent to the circle, this is the tangent to the circle, is perpendicular to the radius that touches the circle at launch point, or to the radius that is drawn to the launch point. The launch point is here is point S, so the tangent is perpendicular to the radius at the launch point. Okay, so here we have 90 degrees. This is a right angle because the tangent is perpendicular to the radius that is drawn to the launch point, according to rule number 1. And here also we drew a radius that is drawn to the launch point. Actually this radius touches the launch point, that is point M. Therefore, according to rule number 1, this is a right angle, and also this is a right angle, and also we have the third radius that is drawn to the launch point. Actually it touches the launch point. The launch point is point Z. The radius touches point Z. Therefore, according to rule number 1, the tangent to the circle is perpendicular to the radius. So this is a right angle. Okay, so actually we created here a quadrilateral QZMD that has three right angles, and we have rule number 2 that states that the sum of the angles of a quadrilateral equals to 360 degrees. Okay, so we have three angles that are right angles, so in total the sum of the three angles is 270 degrees, and the fourth angle must complete the sum of the four angles to 360 degrees. So the value of the fourth angle will be equal to 360 degrees minus 270 degrees. Okay, So the value of the fourth angle equals to 360 degrees minus 270 degrees equals to 90 degrees. So we actually proved that the fourth angle is also a right angle. So we have here a quadrilateral that has 4 right angles. And therefore, according to rule number 3, that states that if a quadrilateral has 4 right angles, then it is a rectangle. According to rule number 3, quadrilateral QZMD is a rectangle because it has 4 right angles. Okay, quadrilateral QZMD is a rectangle because it has 4 right angles according to according to rule number 3. Okay, so we have here a quadrilateral QZMD is a rectangle, and according to rule number 4, the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other, so QZ is opposite to MD, therefore QZ equals to MD. And we know that QZ equals to small r, so MD that equals to QZ will be also equal to small r. Okay, so we proved that MD equals to small r. Okay, and we repeated on the same process on the quadrilateral SQCM. Quadrilateral SQCM has 3 right angles. So according to rule number 2, the fourth angle must be equal also to 90 degrees because the sum of the angles in a quadrilateral equals to 360 degrees. So in order to complete the sum of the angles to 360 degrees, the fourth angle must be equal also to 90 degrees. So we prove that we have here a quadrilateral with 4 right angles, and according to rule number 3, a quadrilateral that has 4 right angles is a rectangle. So SQCM is a rectangle, and according to rule number 4, the opposite side of the rectangle are equal to each other, so SQ equals to CM and SQ equals to small r, so CM also must be equal to small r. Okay, we actually proved that CM equals to small r, and we have already proved that MD equals to small r. Okay, then we defined PM, line segment PM as x, and we found the value of CP. Actually CP equals to CM minus PM. Okay, and CM equals to small r and PM equals to x according to our definition. So CP will be equal to r minus x. Okay, CP equals to r minus x, and then we calculated the value of the radius of the big circle in 2 different ways. We note that AB is the diameter of the big circle, so it equals to 2 times the radius. Actually it equals to AP, that is the radius of the big circle, plus PB, that is also the radius of the circle. So we can write 2 different expressions for the radius of the big circle. The first expression will be that AP equals to the radius of the big circle, because P is the center of the big circle, so AP is the radius of the big circle. And what is the value of AP? AP equals to AC plus CP. Okay, so AP equals to AC plus CP, and we know that AC equals to 9 units and CP equals to R minus X. So we got the expression for the radius of the big circle that equals to 9 plus R minus X, plus 9 plus small r minus X. So this is the first way to calculate the radius of the big circle. And the second way to calculate the radius of the big circle is that the radius equals to PB. Okay, the radius of the big circle equals to PB. So we calculated the radius of the big circle according to the second way, and we got that the radius of the big circle equals to x plus r plus 4, because it actually equals to dB plus md plus pm. dB is 4 units, md is small r, and pm is x. So in total it equals to 4 plus small r plus x. Okay, so we have two different ways that we calculated the radius of the big circle. Okay, so that is the two expressions for the same radius. So actually equation number 1 equals to equation number 2, because it is two different ways to calculate the same radius. So equation number 1 equals to equation number 2, and in this way we created equation number 3, and from equation number 3 we got the value of x. We found out that x equals to 2.5 units, and then we substituted x from equation number 1 by 2.5 units, and we got the radius of the big circle equals to 6.5 plus small r. Okay, so that is the first expression for the radius of the big circle, and we presented the rule number 5, and we implemented rule number 5 in our circle. Rule number 5 states that if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so whenever we have two circles with internal length between them, then the distance between their centers equals to the difference between their radiuses. Okay, so here we can implement rule number 5 in our circle, because we have two circles with internal length between them. They touch each other internally at point N. Therefore, according to rule number 5, the difference between their centers, that is to say PQ, equals to the difference between their radiuses. That is to say PQ equals to capital R minus small r. From here we got equation number 4 that states that capital R equals to PQ plus small r, but we have equation number 4, equation number 1 that states that capital R equals to 6.5 plus r. So we have two expressions from the same radius, so they of course equal to each other. So we compared equation number 1 to equation number 4 and created equation number 5. And from equation number 5 we got the value of PQ that equals to 6.5 units, and we already know that x equals to 2.5 units. Okay, so we connected together points P and Q by a straight line, and we created a right triangle. The green triangle is a right triangle because angle QMP equals to 90 degrees. And we found out the value of QM, that is the radius of the small circle, according to the Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say QP square equals to PM square plus QM square. QP square equals to PM square plus QM square, but we know that QP equals to 6.5, units, PM equals to 2.5 units, and the only missing variable is R. So we solved this simple equality and we found out that the radius of the small circle equals to 6 units. Again, the radius of the small circle equals to 6 units. Okay, thank you very much.